started. So I think we're going to wrap up these slides today. Yeah, plenty of time. So qualifiers and quantifiers. Quantifiers are the mathematical new logical operators that we learned, the for all and the there exists. And they are a little bit complicated, I will give you that. They're one of the main topics of a computer science class that we teach here that is like, it requires 2 prerequisites. So if you're understanding this at all, you should give yourself a pat on the back. It's a fun idea though. So we've learned how to make statements that look kind of like this. Like for every index I, L of I is less than or equal to L of I plus 1, and that means that that was this one up here, right? That was like a list of numbers is sorted. That's what that translates into if you think about it long enough, which is cool. So let's come full circle. Let's keep going with that thought, and let's try to figure out how to go from an English-looking statement, something that I'd like to say and make formal and eventually prove, to math. Let's turn it into a statement with quantifiers so we can get practice with that. And then, almost magically, one way to prove something that you are arguing, one way to make a proof is to write a program, actually, which is kind of cool. So I'll show you that. We're going to prove some of our statements that we write today by writing a program to show beyond a shadow of a doubt that this thing is true. It's kind of cool, or false. So we need some more terminology to get there. Let's start with predicate, the idea of a predicate. And PowerPoint loves me, and so it always resets this stuff. Let me fix it. There we go. So a predicate is a new word. It is a proposition. It's a special kind of proposition, and we got to remember what that is. So a proposition is just some sentence that you have that is either provable to be true or false. Something that could be true or false. I guess you can have unprovable propositions, unsolved problems, but it should be either true or false, not both, or neither. Something that is true or false. That's a proposition. And a predicate is one with variables in it, right? So you have variables that could stand in for some things, all right? So let's see here. So just a normal proposition is something like, it's raining today. I think I did see on the weather that it rained a slight amount yesterday. Like it kind of smelled like it did. I don't know if it really did. Did it? Oh, nice. So maybe this is a true proposition then. It's raining today. So it did rain, perhaps, depending on where you were. So maybe a couple days ago, though, if you asked this question and you said it's raining today, it would have been a false statement, right? So that's a false proposition. So a predicate is just a proposition, but it has variables in it, so it's not yet true and not yet false. You'd have to fill in the variables to know if it were true or false. So here's an example proposition. We'll call it P. That's very common in math. So P of X is a proposition involving X, and we're going to define it to mean that X has a cat. X has a cat. So it's from X's perspective, a cat. And you see how this is not true or false, right? Because we don't know who X is. Some people have cats, some people don't have cats. So you have to fill in a value for this variable for it to become a proposition. I hope that makes sense. All right? So you can fill in somebody and be like P of Lawton and ask for that. P of Lawton is true, right? Because I have a cat. Maybe P of you is false if you have dogs instead or something. So that's what a predicate is. This is like an almost proposition. It has some variables that you could fill in, and it will become a proposition that you can then go and see if it's true or false. All right, so that's a new term. And every single one, I shouldn't just say many, every single one of our quantified statements needed a variable. That's what it means to introduce a quantifier. You're always saying something like, for every X, something involving X, some predicate involving X is true. All right, so actually, if we use our current P, and I say for all X, P of X is true, what does that mean? If P of X is X has a cat, I'm saying for every X, P of X has a cat, right? Or X has a cat. For every X, P of X is true. That's equivalent to saying that everyone has a cat. Claiming that. And that's a false proposition, right? So essentially, a quantifier is a way to take a predicate and turn it into a proposition. This is true or false, right? This is a true or false statement. Everyone has a cat. It's a false statement, really. But P of X by itself, it's like, I'm not yet something I can prove. A quantifier makes it so that you can prove it, which is kind of cool. Does everybody see how for all x p of x for this definition of p means it's trying to argue that everyone has a cat? That's what it translates to. So that's kind of fun, new symbols. So I guess our main goal of these slides and most of the logic slides is like we have something that we're thinking about that we want to prove. How do we say it precisely so that there's no ambiguity and like everything works out in the end? That's the goal. So I'm just going to give you a bunch of examples to try and figure that out. Right? So here's an example thing that we're going to go all the way for. We're going to take it from English, translate it to math with maybe some quantifiers, and then prove it with a program. So that'll be fun. So here is a statement, right, I can make. There is a prime number that is greater than 50. That's a proposition. It could be true or false. I think it's probably true, right? So if we would like to specify this in math, we'd like to go from English to math. What do we got to do? Well, we have to talk about this thing, right? We're trying to say that there's a prime number that's greater than 50, so we got to give it a name and then talk about it. That's always important. So we got to call that number x, let's say, all right? And then we have to write down exactly what is true when about x for this to be the case, okay? So here's what's true about x, right? It's x is greater than 50, and it's prime. That's what this statement is saying. If there was an x, then it's greater than 50 and it's prime. That would be true about that x, okay? So this is almost math, kind of, right? It's like there's an and, we know that. And this is just a statement about this x. Not true or false yet because we don't know what x is. There's a variable involved, so this is a predicate. That's the idea. So that's a predicate. And we can go even a bit further. Let's import this little and symbol, and we'll use some more mathematical notation. This is pretend we have like a function that gives back true if the number is prime and false otherwise. So that's the idea. Let's pretend we have like a prime function, and we can use that in math. So prime of 5, for example, that would give back true. Prime of like 6, that would give back false, of course, because that is not a prime number. So, okay. This is what's true about that x if there is one. We're trying to see, is there a prime number that's greater than 50 right now? We're trying to prove, or at least make the statement that there is one, okay? So, what's true about it? Call it x. It's greater than 50 and it's prime. And so this, I guess you can think of this little function as a predicate in itself, isn't it? Itself a predicate. Because you give it something and it tells you if it's true or false, if that one thing was prime or not. Itself a predicate. So you can build up bigger predicates with smaller ones. That's kind of what we're doing here. Predicate, and then stray dot. Let me get rid of that. It would bother me otherwise. All right, so now we're almost there. There's a quantifier that needs to go in here. Which one is it? Is it the upside down A or the upside down E? We've got, as our options, for all and there exists, and I think it's the second one, yeah? So if we really wanted to make this mathematical, we needed to introduce a there exists, and if we think about it, right? If we can find some x, right? There exists some x, such that, ST stands for such that the thing above is true for that x, then we have a statement that we can prove something to be true or false, and it's this one, all right? So that's the full story. This is the mathematical equivalent of this English up here. There exists, if there is a prime number that's greater than 50, this translates to this. There exists an x, that can be our prime number, right? Such that it's greater than 50 and it's prime. Okay, that's precise, that is mathematical. This is now, by introducing a quantifier, turn this into a statement. This is a statement, it's also a true statement, right? Because 51 is not prime, that's a multiple of 3, right? Maybe 53 is a prime, though. This is a true statement. We still have to go and prove it, though, but we know it to be true in our hearts, right? So this is now a proposition. Before, this is a predicate, right? It just was dealing with an x that didn't exist. But now, once you introduce a quantifier that quantifies over that variable, we've turned it into something we can prove, true or false. So this is now a proposition. Whee. So are there any questions about how we went from this English to this math? Does that make enough sense? There exists an x such that x is greater than 50 and it's prime. That is the equivalent of this English here. So I guess the last thing that I want to say on this slide, I don't know why I have to hide it from you, but here, it's the last thing. Every single quantifier, every time you use a quantifier, you have to introduce a brand new variable. And that's what it's quantifying over, we say. All right? Every quantifier introduces a variable. It kind of like gives something for the variable in the rest of your math to hold on to reference. And so that turns this rest of the stuff into a proposition from a predicate. It's a good way to go from a predicate to a proposition. That's that. And I will underline that so you remember it. So that's a there exists kind of problem. And let's prove this now. This is a true statement, right? This is totally a true statement. Let's prove that it's a true statement. What does it mean to prove that there exists an x such that x is greater than 50 and it's prime? Well, really, we just got to find one, right? If we just find a prime number that's greater than 50, we have proven this predicate or this proposition to be true. Does that make sense? If you show me that number, give me an x, tell me that's greater than 50, prove that to me, and prove to me that it's prime, and then, yeah, it checks out. So let's do that. Let's find a prime number that's greater than 50, and we can write a program for this, can't we? This is how you can turn a program into a proof, essentially. You can use a program to write a proof. So we just got to think of an algorithm, some strategy to prove this thing. We just got to go start searching, right? Start searching through numbers that are greater than 50 and see if we can find a prime. Because if we just find one, we've proven the statement. Okay, that's the goal. So let's see here. Let's assume, first of all, that we have like an isPrime function. We're eventually going to program that. But assume that we have it. Like we can call it on a variable or a value. Be like, hey, is isPrime 42? What is that? It will give back false because it's not prime. Right? So pretend we have that in Python. And then the goal is, right, just like start at the number 51, check if it's prime. All right, if that's not prime, make it 52. Check if that's prime. If that's not prime, make it 53. And just keep on going. Because we know that there's infinite primes. Hopefully, this will stop and tell us, oh yeah, I found a prime number that's greater than 50. But just like set a variable or something, start it at 51 and just start searching. If 51 isn't prime, try 52. 52 isn't prime, try 53. Right? Does that strategy make enough sense? Like if this ever stops, if it ever finds a number, then we've proven our theorem, which is so cool. All right, so here's the pseudocode. It's not actually Python. It's like English-looking code. It's called pseudocode for this algorithm. So it's just like go through the numbers, iterate through all the numbers, starting from 51 with like a while loop, the loop that we know how to do, and then like call it I. Have an I variable that does the ranging, and then if I is ever prime, stop. There's a quit function in Python that stops the loop. So or stops your whole program, in fact. That could be what we use here. And because we started at 51, we know that 51 is greater than 50, and if we keep on incrementing, it'll never get smaller than 50, so that's true to start with. So if this ever stops, if this code ever stops, then it found a prime greater than 50, and we've proven our statement that there exists a prime greater than 50, right? Kind of a contrived example, but I hope it makes at least a little bit of sense. How you can write a program that does this. So let's do that. Let us write a program that finds that value, all right? So I'm going to open up idle on a Monday. Wow. And let's see, what lecture are we? We are lecture 21. So I'll make a new file and a new folder for us. Let's see here. So we're lecture 21, and I'll make a folder for that. And I'll call the file, though, square root proof.py. So let's see if we can code that pseudocode up. Let's make it real code, real Python. So the goal is to do this. We want to iterate through every number with a while loop starting at 51. We'll call the number I. All right. Oops. So it'll be like I equals 51. Right? Something like that. Oh, I'm sorry. It's not square root proof. Sorry, I was looking at the other program. Excuse me. That's our next program. I'll keep it open. Why not? New file. This is prime program. Sorry. I was thinking ahead. Prime greater than 50. There we go. So I'll come back to that one. Sorry. I'm getting ahead of myself here. All right, so we got 9, and we're going to start it at 51. And then we just want to continue until maybe the end of time. If there are no primes greater than 51, we just don't want this to stop, because if it stopped, it would say that it worked. So I'll say while true, that makes a forever loop, right? Never stop, unless I tell you to. And so we have an I that we're working with. Let's check if it's prime. Check if I is prime. If it is, print it out and like stop the program because we found one. We're just looking for one good one that's greater than 50. This will find the smallest one. Otherwise, increment I, and so that we can like check the next value. Because the first one will not work. 51 is 5 plus 1 is 6. That's multiple of 3, right? So it'll divide into 3. So that's not prime. But maybe the next one is 52. Oh, no, that won't work. Then 53. I think 53 is going to be the prime, if I remember correctly. So let's code this up. Let's pretend that we have an isPrime function, and we're going to have to add an if statement. Let's see if I can get all this on one screen. So check if I is prime. If isPrime of I gives back true. You can check it like that, equal true, or just like it's going to be replaced with either true or false. Just use that. If isPrime of I becomes true. Think of it that way. And then if it is, like we want this to be indented, print it out and stop the program. So it'll be like print I, and then there's a function called quit in Python that just stops your program. So it'll stop this infinite loop that we were going through. Otherwise, if we didn't hit this if it was false, we didn't continue, or we didn't go through this if's body and we didn't stop the program. So let's just come back around. Let's increment I equals I plus 1, so that now it's like 52, 53, 54 until this if statement works on that I. That's the goal. Try a new one. So does that setup make enough sense? If this ever stops, it will have found a prime that is greater than 50, and that is what we want. All right, so let me actually show you how to make a function in Python very, very quickly. I'm not teaching this to you yet. I just need it now because there is no like math library isPrime thing. So you can look away if you would like, but here's how you make an isPrime function. I'll show you the syntax as like a sneak peek for later, and then I'll talk about the algorithm right now because that's kind of cool to think about. What does it mean? Like we want a function that checks to see. We want some code that checks to see if a number is prime or not. What does it mean for a number to be prime, right? So a number n, call it n, is prime when it has no factors other than 1 in itself, right? That's like the mathematical definition. Let's try and think about how we could code that, though. A number is prime when you try to divide it by 2, you try to divide it by 3, you try to divide it by 4, you try to divide it by every number that's not 1 in n, right? And none of them work. Don't divide cleanly. Does that make sense? That's what it means to be prime. That's how you could check that. Cleanly into n. So like the number 4 is prime because you start with checking 2. 2 divides cleanly into 4. There's nothing left over. So that is not a prime number. But 5, like you try 2, 3, and 4, none of them divide cleanly into 5. So 5 must be prime. That's the goal. So that's the idea. And it'll just be a loop. Like loop through these numbers, try to divide it into your number, and if none of them come out cleanly, there's always a remainder, then it is not prime. Then it is prime. If you find one that works, like it divides in and there is no remainder, then it was a composite number. So let me show you how to make an isPrime function. Feel free to look away if this scares you, but we'll eventually show you how to do this for real. You say def to make your own function. You say def, and then you give its name. I'm making an isPrime function, and the variable involved as your argument is going to be, I'm going to call it n. Then you put a colon like everything else in Python. So here's what I'm going to do. I'm going to try to divide by 2, 3, all the way to n minus 1, and see if any of them going cleanly. If they do, it's not prime. So I'm using I down there. I'll use j here. So I'll start j at 2. While j is less than or equal to n minus 1, I'm just going to have it keep on doing stuff. So try to divide n by j and see if it worked out. If it did, it's not prime. And then keep on advancing while I'm still looking, while I've got room. J equals j plus 1. So that'll iterate j between 2 and n minus 1. I want to try all of those. Try to divide n by that particular j each time. So here's how you check if the division went in cleanly. You say if that number mod, use the modulus, mod j is equal to 0. And that's saying if you try to divide n by j and give me back the remainder, if that remainder is 0, that means there's nothing left over. It went in cleanly. So j divided cleanly into n. So j is a factor of n. And primes can't have factors, return false. So that's how you say, immediately stop this. I found my counterexample, it's false. Otherwise, keep searching. And if we get through this whole loop and we don't find a factor, if we get here, there were no factors. It must have been prime, that n. So return true to whoever called me. And so that's the isPrime function. I don't want to say much more about that. I'll show you how to make your own functions later. But we could use that, and then it's like, all right, I'm going to try my values. It gets past 51. It's like, that's false. Try 52. Gets past 52. It's like, that's false. Not prime. Make I 53. And then it tries, is prime of I? And what do you know? 53 is prime. It gives back true. So it prints the I and calls quit. And idle is like, are you sure you want to stop the program? And I say yes. There it goes. And so that's the idea. Are there any questions about that? I don't want you to understand the isPrime yet, but does this code make enough sense? We're searching for all the values until it works. And so that means we found a value that's greater than 50 and is prime. And so we've proven this statement. We've proven that there does exist an x such that it's greater than 15 prime. 53 is one example. That makes that a true statement. Cool. So that's fun. All right, I have another example that has to do with square roots. And that's what I was thinking of when I made the first file name. So we'll go back to that now. So here's another proof that we can make. Let's prove that for every number, every integer, call it n, between, let's say, I don't know, 0 and 100, the square root of n is less than or equal to 10. Is that a true statement? Well, here's the graph, right? What's the square root of 0? That's just 0. What's the square root of 100? It's 10, right? And the square graph grows like this. So is it ever bigger than 10 between 0 and 100? I do not think so. So this is a true statement right now. So it's something we could prove. Cool. And so let's figure out what the mathematical thing is that we would go and prove. Because this is just English. How do we prove this? Convert it to math so that we can maybe write a program that proves the thing. All right, so let's first convert this to math-like English. We have to change this idea. For all integers, call them n between 0 and 100, and square root of n is less than or equal to 10. So that's very close already. We can just replace the for all with the for all symbol. That's fine. But there's more involved. So here is, let's say that we already have an n. All right. How do we say that it's between 0 and 100? That's the only n's we're considering. that actually becomes an if-then statement in math. It becomes an implication. Sorry. If and then that corresponds to our implication symbol, right? And this is how you say, the n that I want to consider, the values that I care about are between 0 and 100. It's just if your n happens to be greater than or equal to 0 and less than or equal to 100, see how that constricts it to be the values that we care about? If that's true about your n, then here's what I expect. Then here's what I want to show you. Here's what I want to argue is true, right? And so this is being very careful. It's not saying like, oh, if n is 101, this is also true. No, it's trying to constrict the values, the range. So if n happens to be within the range that I'm trying to talk about, if n is greater than or equal to 0 and it's less than or equal to 100, then its square root is less than or equal to 10. So do you see how this kind of translates between this and our if-then statement? Now it's getting closer because we know how to translate that into an implication. And so let's convert this to full-blown math, because this, like, we've got an and, right? Let's do that. So if this is true, if n is greater than or equal to 0 and n is less than or equal to 100, then the square root of n is less than or equal to 10. So remember that this implication symbol is saying if the thing on the left is true, then the thing on the right is true. It's our mathematical if-then statement. And this whole thing now, it's involving some n, and it depends on the n, right? If it's true or false. And so that, by definition, is a predicate. Cool. We're getting there. And we want something we can prove true or false. We want to range over some n's, all right? So let's add in a quantifier. For all integers n, for which this is true, I want to say that the square root is less than or equal to 10. And so we're going to add in the quantifier, and that will give us our final mathematical idea that we could then talk to other people about. They would understand exactly what we wanted, what we're trying to say, without any ambiguity, and then we can go and prove it too. All right, so this is saying for all n, that's how you read it. For all n, if n is greater than or equal to 0 and it's less than or equal to 100, so that constricts it to be within the range that we care about, then, right, then, if that's true, then the square root of n is less than or equal to 10. You see how I'm reading that? And here's that in English for posterity's sake. For all n, if n is greater than or equal to 0 and n is less than or equal to 100, then the square root of n is less than or equal to 10. Do you see how this is equivalent? All this stuff, that's equivalent to this statement up here, just mathematical informal. Are there any questions about that translation? All right, because now I have a question for you, and you're going to do very similar things to what I just did, so I'll give you this code in just a second. Here, I'll just paste it right now, why not? Whee! So here's this. And I'll paste it here. So you're going to do something similar, right? See if you can do this. Create a program. Write a program, or at least write down like pseudocode somewhere, but try to do it in Python if you can. Write a bunch of comments that proves that this is true. This is a true proposition. That's that formula we were trying to prove. Can you figure out how to write a program that can go and make sure that this is true? For all n, if n is greater than or equal to 0 and it's less than or equal to 100, then its square root is always less than or equal to 10. Pretend that n is only a whole number. Assume n is an integer that we're talking about right now to keep it easy on yourself. But you're going to need to use square root, and that lives in the math library. So let me show you that. You have to say import math. Remember that? Say import math, and then you have access to the math library, and it's math.square root. Math.square root to actually go and use that, and you can like give it a variable, give it a number, and then it'll go and compute the square root, because you're going to need to compare that square root, won't you? All right? So do you see a similar kind of thought to what we were doing here that could go and prove this statement for every n that we cared about? So go and try that. I've got plenty of time. I'll give you several minutes. And that will do it. The first line is probably going to have to be import math, so you just use that everywhere else. You can be the variable that you use as your ranging. Just like I was using I in this code. A couple more minutes and then I'll show you my answer. Kind of want to check for the opposite thing, I think. It's like, if it's greater than 10, then you found a bad thing. You know, it's immediately not true, right? Kind of have to wait. You got to try them all, right? Got to try them all to know that it's true. Which is a little bit different than the other proof. We're just looking for one good one. And there exists, but for all, you got to wait until the end to see if they all worked. But you can bail out early if you find one that doesn't work, because they're all supposed to work. It's a for all. That's my very loud alarm. Alright, so let's break this down. I assume you figured out what to loop through, but let's have a slide dedicated to it at least. Did any questions come up though as we were trying this? That will not be answered by me showing you the answer or my thoughts. Alright, so kind of the idea is we want to try every number like between 0 and 100. Let's pretend that we're only talking about integers to keep it easy on ourselves. But the goal is like, alright, loop through every number n between 0 and 100 because those are the ones that we care about, right? We got to check this about all of them. It's like start n at 0, have it go between 0, 1, 2, all the way to 100, and then just keep checking. For each n, like square root of 0, square root of 1, square root of 2, all the way to square root of 100. Yeah? And then we just want to keep seeing that, confirming that it's always less than or equal to 10. If it's true for all of them, then we've proven it. Yeah? Kind of the goal. So, it's easier to think about this backwards. It's like, it's got to be true for all of these guys. The second you find something that's bad, something that's bigger than 10, then it didn't work. We know immediately that we didn't work. That's called finding a counterexample, right? So if the square root of n, as we're looping, ever gets greater than 10, then we can just stop immediately. Like, we found a bad value. It's obviously, if it's not true for this one, it's not true for all of them. So, because that one's included. So we'll just stop early if that's ever greater than or equal, or sorry, greater than 10. We're checking to make sure that they're all less than or equal to. If it's ever greater than, we're done. We immediately know that it's a false statement, all right? But if this loop ends and we never complained, then we can print true and say we're done with it. Okay? That's kind of the goal. That's my strategy. Did you come up with something similar? Something completely different, maybe? That's kind of my idea. And so here's my file, square root proof. And let's do this. Let's loop through every number, call it n between 0 and 100, and see if we can get the right stuff printed. So I want to import math so that I could run the square root function. And then I'm going to start my n at 0 and just keep on working while n is less than or equal to 100. So I want n to range between 0 and 100 exactly. Okay? And just advance n equals n plus 1 each time at the very end. And so the goal is, as n is ranging between, right now it is ranging between 0 and 100, as it's doing that, check and see every time for that current n value, hey, is that one greater than 10? Is that one greater than 10? Because it's like making sure that they're all less than or equal to, as long as they're not greater than, right? So if math.square root of that n, whatever it is, maybe it's 0, maybe it's 100, it's ranging through all of those guys. If it's ever greater than 10, oh no, print false. And then we can like quit to stop the program, stop early if we'd like. So that's the goal, n equals n plus 1. So if it's ever greater than 10, like we immediately have found a bad value. They're all supposed to be less than or equal to. So it stops, and it's a false statement. We've disproven our statement if that's ever true. But if this gets through and we never stopped the program, that means they all worked. Like we never hit the body of this if, which meant they were all less than or equal to 10. Which means if we ever get here, then the statement must have been true. Nice. So that means we can print that it was true. And so we will be trying all those values if I run this. And it does print true. Yay. Are there any questions about that? Why this code? Am I missing a line? No, it's just import math, right? Yeah. Why this code is going to prove beyond a shadow of a doubt that every number integer between 0 and 100, call it n, is less than or equal to 10. Any questions about that? It just told us, yeah, it's a true statement. It worked. So that's the full story. Going from math, from English to math, using that to write code to prove or disprove a statement. It's beautiful. Yay. So let's say we had a false statement, like one that we could disprove. Let's say that we were trying to prove that for every number n between 0 and 101, this is true. It's a bit bigger, right? If you do the square root of 101, it's definitely bigger than 10 by then. So this would be a false statement. And let's watch our program correctly discover that it was a false statement. So we'd have n range between 0 and 101 this time, but for that last value, it would notice, like, oh no, false, and it would stop. Any questions about that? This is like, it's a very generic kind of program. It works very well for all the options. But this is going to prove our statement. Any questions about any of that? So that's the range from English to math, and then certain programs you can write for certain statements. You can write a program to prove that it was true or false, which is so cool in my mind as a computer scientist. All right, so the moral of this story is that logic and computer science, they are coupled in a way that is very powerful. You will have to wait until an upper division or like a graduate level computer science class if you want to fully appreciate this idea, but at least I hope you can see little glimmers of these facts right now. So we have logic, which we think of as on paper, but computer science kind of gives it some more meaning, which is kind of cool. And so if you think about both, you think logically about how you're writing your stuff. You try to translate from logic formulas to code that helps you write correct programs because you were thinking logically and trying to get it right the first time. And then you can also use that same stuff to argue why, like, your programs that you've written before, like, you can prove that, oh, this is going to do the right thing, or prove that it was always going to mess up. So that leads to program verification, which is another very complicated topic in computer science, but you know enough to at least appreciate it now. So I think that's all that I want to say for these slides. Any questions about any of that before I talk about your next writing assignment, since it is a Monday? All right, so let me release this. This will be a 2-week essay for you, since we're in week 12 right now. But you got one due, so I got to give you another one, of course. All right, so this is a very open-ended assignment, I think. 750 words, so not as long as the last one. Get a little bit of a reprieve. So here's your prompt. Go and pick your favorite painting, or find one if you don't have one. Go and pick a painting that you really like that was made sometime before 1900, all right? It's like a Renaissance painting, an Impressionist painting, something old before 1900. Okay, that's very important. And then pretend that the artist who made that painting that you like so much, so long ago, pretend that they were alive today, and they made that same painting on a computer. Right? They made it using today's technology. Like, they used a drawing tablet like I do. They used Photoshop for all their virtual brushes and stuff. So they're like still painting. They're just virtually painting. Would you consider that painting to be just as beautiful as you do right now? Okay, if they made it digitally. Please tell me why or why not, and explain your thoughts. Okay, does that prompt make sense? It's very open-ended, but at least I get to learn what kinds of paintings you guys like. So please write a 750-word essay in response to that, and please cite at least one work as you are arguing your point. All right, so I found some cool sources. Let me know if they don't work, and I'll fix them. But that's that, and it's possible that you are not very big into art or digital art. So here's 2 people that I follow on Instagram, 2 digital artists that kind of show you both ends of the spectrum. Like, this first person likes really cartoony stuff, and the second person, they just disabled their account. I remember that. Oh man. So I'll try and find them in a different way and link to them, but they're cool. They're very real. They have a lot of realism. I'll just link to his website maybe. But this person, she makes very like abstract kinds of art, and I enjoy it. So that's one side of digital art. And then here's another side. This is like very realistic. This guy's very famous for his work, and so maybe I'll link to his website. And so like this looks real. That's what he paints digitally, though. So okay, that is those are some examples, and I think that is all that I wanted to say. So that's your prompt. Please remember to cite that work and tell me if you would enjoy that painting if it were made today. Any questions about any of that? All right, so I think that is all that I want to say. So this will be due in 2 weeks. So you got some time to get started on it.